Any questions on this question? Okay, and the other question was fairly straightforward. Almost everyone got the answer. So let me just check what was the question. Yeah, so you had to find. So you were given a polynomial. You had to find minimal primes of the So you had to find irreducible component of the zero set of this polynomial, and you also had to find minimal primes containing that minimal primes of the ideal generated by that polynomial, and you also have to find the radical ideal. So all the three are obviously more or less the same question. So the polynomial, you just factor the polynomial and into irreducible factors, and each irreducible factor corresponds, since you are in a UFD, irreducible factor gives you a prime ideal, which generates a prime ideal, and and of course the irreducible factors gives you irreducible irreducible subset of the zero set of this polynomial. So that gives you certain number of irreducible subsets, and these irreducible polynomials, the minimal polynomial the prime generate which these irreducible factors generate are the minimal primes. Yeah. So you can prove it more directly, or you can use primary decomposition. You can even prove it directly, because it's product of this polynomial is a product of something which belongs to a minimal prime. So one of the factors have to be in there because it's a prime, and that tells you these are all the minimal primes. And then for radical, you just have to take the intersection of these minimal primes to compute the radical. Okay, so I'm not going to work that out. I think that's pretty straightforward, unless someone wants me to. Okay. So, any questions? Okay, so I'll move on to the lecture if there's no other question on this. Okay. So last time we were talking about going up theorem. So I stated the going up theorem, and we talked about this lemma. So we proved this lemma, which we will use in the going up theorem. So this is where essentially this integral extension comes into play. Yeah. So A contained in B be integral extension, Q contained in B be a prime ideal of B, and P is the intersection of Q with A. So P will be also a prime ideal. Then you can conclude that Q is a maximal ideal of B if and only if P is a maximal ideal of A. So when you have integral extensions, then maximal ideal contracts to maximal ideal. Okay. So we saw we already saw the proof of this lemma. So we'll use this lemma to prove going up theorem. And so the going up theorem says, so it will help us prove some dimension kind of statement. So for instance, we'll show that if A to B is an integral extension, then dimension of A and B are same. Okay, for instance. So what is going up theorem? So let A contained in B be rings with B integral over A. Let P1, P2 up to Pn be a chain of prime ideals in A, and Q1 to Qm be a chain of prime ideals in B, such that Qi intersection A is Pi for the first m guys. Then you can say that there exists Qm plus 1 to Qn prime ideals of B, such that Qi contain intersection A is Pi. And so maybe one thing which I probably missed, with QM plus 1, so this containment relation is still holding. Yeah. So QM plus 1 contained in next guy and so on, and everything contains QM. Okay. So this is what going up theorem says. Okay. So we'll see that, this is the way it's written is made for induction. So what we'll do is we'll prove the base case and see that basically the base case works. So meaning the base case is lying over theorem. Yeah. So let A to B be integral extension of rings. Let P contained in A be a prime ideal, then there exists a prime ideal Q of B such that Q intersection A is P. Yeah? So this is in some sense special case of going up theorem where M is 0 and N is 1. Yeah. So there is no hypothesis on the chain of prime ideals, and you just, so given any prime ideal in A, there exists a prime ideal in B such that that contracts to the given prime ideal in A. So it's a special case of going up theorem, but we'll see that this is essentially what you have to do. Okay. So let's see, in fact, you can even assume A and B integral domain to prove this going up theorem. Okay. So maybe I don't remember since it's been a while. I prepared this more than a week ago. So I don't know if I use integral domain or not. So we'll find out, yeah. So let's prove the lying over theorem, and then we'll use it to prove going up theorem. Okay, so so I don't think we use integral domain here. So let S be the complement of the prime ideal, the given prime ideal of A. We want to find a prime ideal of B which contracts to A. Yeah. So the easiest way is to make sure that prime ideals which are too big, you just kill them, and the way to do it is just invert things outside P. Yeah. So that is what we'll do. So remember, complement of a prime ideal is a multiplicative set. Yeah. So S is a multiplicative set, and S is not only contained in A, but it's also contained in B because B is a bigger ring than A. Yeah. But multiplicative set has nothing to do with what the ambient looks like. Yeah? So S is a multiplicative set in both A and B. And since B over A is integral extension, S inverse B is an integral extension of S inverse A. Yeah. So this we saw last time, that when you localize both the top guy and the bottom guy, then it stays integral. Yeah. So in general, S inverse A won't be integral over A. Yeah. But or S inverse B will not be integral over B, but S inverse B will be integral over S inverse A. So I mean, basically you use the same. So if you have some B over S, so B will satisfy some integral equation over A, then B over S will satisfy some integral over extension, integral equation over S inverse A, because you sort of adjust the denominators. Okay. So this is an integral extension. Now let Q tilde be a maximal ideal of S inverse B. Yeah. So so if you take any maximal ideal of S inverse B, now by the lemma which we have proved, if we contract it to S inverse A, if we intersect Q tilde to S inverse A, it must be a maximal ideal. Yeah, that is what the lemma says. Yeah, so you look at Q tilde intersection S inverse A. By the way, what is S inverse A? S inverse A is A localized at P. Yeah, because S is A minus P. So not S inverse A is by definition is same as A localized at P. It's the local ring A with the where you sort of invert everything outside P. Yeah. So this, I suppose you must have seen in your Algebra-3 course that this is a local ring with maximal ideal PAP. Yeah. So by the lemma, Q tilde intersection A localized at P is PAP. Yeah, because it has to be a maximal ideal of AP, and there is only one maximal ideal of A localized at P. Yeah. So now we have the candidate. So remember S inverse B is something bigger. So you have a map from B to S inverse B. Yeah, the natural localization map. So you can take the intersection, or you can. So intersection is somehow sometimes. So intersection really means the inverse image. Yeah. The contraction. That is the convention we have been using. Yeah, so, but if it's domain, then you don't have to worry about all that. You can actually do it on the. You can actually call it an intersection. Otherwise, you look at the inverse image of this natural map from B to S inverse B, which sends B to B over 1. Yeah. So Q is Q tilde intersection B, or inverse image of Q tilde in B. Now the claim is Q intersection A is P. Yeah. So let's just pretend that we are in integral domain. Anyway, we'll use this Langover theorem over integral domain. But you can do it rigorously as well without assuming it to be an integral domain. And anyway, we'll prove going up theorem without any such hypothesis, integral domain hypothesis. So it all works out. Okay. So the claim is Q intersection A is P. So note that Q is going to, since we have contracted a prime ideal of a maximal ideal of A, which in particular is a prime ideal of A localized at P, Q is a prime ideal of B. Yeah. So if we show that Q intersection A is P, then we are done. Yeah. So let's just check that. So Q intersection A by definition is Q tilde intersection B intersection A, because Q was Q tilde intersection B. And of course, A, B, and Q tilde everything contains P. So Q tilde, remember Q tilde intersection A localized at P is PAP. So P is contained in everything. Yeah. So this Q intersection A contains P. So that part is straightforward. We just have to prove the other inclusion. Okay. So let X belongs to A minus. So we'll prove the contrapositive. So let's take contrapositive. So let's take X not in P. Then we will show that it does not it does not belong to Q intersection A. Yeah. So that will show that if something belongs, so if something belongs to Q intersection A, then it must belong to P. So X belongs to A minus P, then of course X belongs to S, which means X over 1 will not belong to Q tilde, yeah? Because Q tilde is a proper ideal of this S inverse B. Yeah. So you can't, and X is a unit in S inverse B. So X over 1 does not belong to Q tilde, which means X does not belong to Q intersection A. Yeah. Hence Q intersection A is contained in. Okay, so I mean the only place we have used integral is in this lemma. Yeah, so this lemma which says which allows us to conclude that maximal ideal contracts to maximal ideal if you have an integral extension. Okay. Any questions? Okay, so if there are no questions, so you guys should ask questions if you are. If you have doubt. Yeah. Otherwise, I don't know. So finally, going up theorem, what we'll do is we'll quotient out by, so we'll use sort of induction, yeah. So we'll quotient out by QM, and we'll use the bijection between prime ideals of B mod QM and prime ideals of B containing QM, and basically you arrange all this and use this lying over theorem, and you get going up theorem. Okay. So it's pretty straightforward. So just once you have lying over, yeah. So what is the proof? So we want to find QM plus 1. So once we find QM plus 1, the rest is straightforward. Yeah, you just use the same method. So remember, we have to find a QM plus 1 which contains QM, and QM plus 1 contracting to intersecting is QM plus 1 intersection A is PM plus 1. That is what the objective is. And we have this chain of prime ideas. Yeah. So all this initial data is just decoration. Yeah. So once you go mod QM, you get a ring B, and remember this ring B bar, and remember B bar is going to be an integral extension of A bar, yeah, where A bar is A mod PM. So A bar is contained in B bar because QM intersection A is PM, and that is precisely the kernel of this composition map. So this we discussed when we were doing that lemma as well. Okay. So hence and of course B since B was integral over A, B bar is integral over A bars. Basically the same equation. You go mod P to get PM to get the coefficients in A bar, and the same integral equation works. Now since okay, so here is the justification. So I guess I've given the justification. So if B bar is in B, then its lift B will satisfy some equation with coefficients in A, and hence B bar will satisfy this this equation with coefficients in A bar. Yeah, so that's why B bar is integral over A bar. Now by lying over, so now remember B bar is B bar contains A bar, and B bar is integral over A bar, and in fact we are all in integral domain as I promised. So hence by lying over, there exists QM plus 1 bar in B bar, prime ideal of B bar, such that QM plus 1 intersection A is PM plus 1 bar. Yeah, because PM plus 1 bar is a prime ideal of A bar. Remember, PM plus 1 was a prime ideal in A. If you go mod, you look at its image, it's going to be a prime ideal in A bar. Yeah, it comes because PM plus 1 contains PM. Yeah, so there is a bijection between ideals of A containing PM and ideals of A and ideals of A mod PM. Yeah. And this bijection preserves prime ideals. So if something is a prime ideal in A containing PM, its image in A bar is also a prime ideal. Yeah. So we can apply lying over theorem and get this QM plus 1 prime ideal of B bar such that this intersection happens. Then you just take QM plus 1 to be the prime ideal, be the ideal of B corresponding to QM plus 1 bar. Containing QM, yeah, which by the way is just Q inverse of QM plus 1, where Q is this quotient map from B to B bar. Okay, and we know that this QM plus 1 is a prime ideal. Inverse image of a prime ideal is a prime ideal. Yeah, so it's a prime ideal of B. It contains QM. And what is QM intersection A? This is Q inverse. So by definition is this. And that is precisely Q inverse of Q bar intersection A bar, which is Q inverse of PM plus 1 bar, which is same as PM plus 1. Okay. So in here, Q inverse restricted to A bar, A one should say. because you are just intersecting with A bar now. Yeah. So it's actually Q followed by I followed by Q. Yeah. So Q composed I. So you get PM plus 1. So that completes the proof of going up theorem as well. Okay, so the crux of the matter is in lying over, and going up is just an induction step. Or rather, going up is the result of induction. Lying over is the induction step. And for lying over also, the crux of the matter is that intersection of maximal ideal. So under integral extension, maximal ideal contracts to maximal ideal. Okay. So finally, so as I said, I want to relate it to dimension of the ring, which we defined last time. So maybe we'll see some corollaries before getting to the dimension. So note that if A to B is an integral extension and I is an ideal of A, if IB is the whole of B, so if I is an ideal such that IB extends to whole of B, then I must be the whole of A. Yeah. So if so all this has a geometric meaning as well. Yeah. So maybe I should talk about a little bit of geometry. Okay. So yeah. So maybe what does P0 contained in P1 contained in P2 mean in terms of geometry? So that tells you that if you look at the zero set of P0, this is going to be some irreducible subset, yeah? If you are in a affine space, or even if in some arbitrary affine. So zero set of P0 is will contain zero set of P1 will contain zero set of P2. Yeah. So it's inclusion reversing, if you remember. Yeah. So this is going to be some irreducible set. So maybe it will. So let's take some examples. So maybe this is some surface. This is going to be. So if this is a proper algebra set, then it's going to be some proper algebraic subset. And so since I mean it could be a point or a curve, but since we don't have too many dimensions to draw, let's just assume that this guy is a curve and this guy is a point. So this is how it looks like. Okay. And what does going up theorem says? It says that if you have this, so if A contained in B is an integral extension, then you have a map from and say everything is over. So everything is A and B are both finitely generated K algebra, where K is some algebraically closed field. Then you can work with varieties and so on. Otherwise, you'll have to work with spec or M spec. If K is just an arbitrary field, if there is no field, then you have to work with spec. So what happens is you have a map from variety corresponding to B, which I don't know what to call it. Maybe XB, yeah. You can call it spec B, but that already has a name. So if you have a map from, so you have a ring homomorphism from A to B, yeah, is the inclusion map. So you have a map from set of maximal ideals of B to set of maximal ideals of A. It is an integral extension, so we already know that maximal ideal contracts to maximal ideal in this case, yeah. And anyway, if they were finitely generated K algebras, then maximal ideal will contract to maximal ideal. So that's also not a problem. Okay. So we have this map, and what does this say? That if you have uh, okay, so let's just translate it what it means. So if you have a picture like this, and in the in above you have a picture, you have a surface which maps to this surface. So that means the pre-image is this guy, uh, and then the first step says that you can find a curve here, whose image is going to be this curve, and you can find a point on that curve whose image will be this point if you have an integral extension. Yeah. So this is what going up theorem says. Okay. So this is what geometric meaning of going up theorem is. So you can find a curve in the zero set in the variety defined by B, such that it maps to the given curve in A, and given a point on this curve, you can actually find a point on the curve you had chosen, which will map to this point. Yeah. So this is how you can translate between geometry and algebra. And what does this corollary say? So the corollary says that if so you look at the zero set of the ideal, zero set of IB. Yeah. So it says that zero set of IB is empty. Yeah. If IB is equal to B, that means there is no element, there is no maximal ideal containing. So it says that if you have an integral extension and zero set of some ideal is empty, that this implies that zero set of I is empty in spec of A. Yeah, or M spec of A if A is a finitely generated K algebra for some field K. Okay. So integral extensions are somewhat nicer, but all this will fail if you don't assume integral extensions. Yeah. So for example, yeah. So maybe I should also give you one example where these things fail. Okay. So yeah. So maybe I'll give you the example after doing this corollary. Okay. So we'll finish this and then I'll do an example. So let A contained in B be integral extension and I be an A ideal. Then as I said, IB equals B, then I equals A. Yeah. So suppose I is a proper ideal of A. So this is a direct consequence of lying over. Yeah. So then there exists a maximal ideal containing I. And then by lying over, there has to exist a maximal ideal of, there has to exist a prime ideal of B containing such that it contracts to the maximal ideal A, but then I is contained in Q. Yeah, because Q intersection A is M and M contains I, so I is contained in Q, which implies IB is contained in Q, which contradicts IB equals B. Yeah. So it's a straightforward contradiction of straightforward consequence of lying over theorem. Then another thing is that if you have integral extensions and Q naught is a and Q naught and Q1 are two prime ideals of B such that Q naught is properly contained in Q1, then their contraction to A are distinct. Okay, so the translation of that is that a curve and a point cannot contract to the same guy here. Yeah. So it can't happen that this curve contracts so when you have an integral extension, it cannot happen that a curve contracts to some point and that point and a point also. In fact, a curve has to contract to a curve. We'll see that the dimensions don't change. Yeah. So that is what the geometric interpretation of this proposition is. So what is the proof of this thing? So you know, A is contained in B is integral extension, and suppose so we have and of course Q naught intersection A A mod Q naught intersection A is contained in B mod Q naught. Yeah, with same principle which we used in lying over theorem or going up theorem. Yeah. This is integral extension of integral domains, and Q1 bar is a non-trivial prime ideal of B. Yeah, because Q1 is a prime ideal of B, and it contains Q naught properly. Yeah, so it is going to be a non-trivial prime ideal, non-zero prime ideal of B mod Q. Yeah, so let's take some non-zero element. So we want to show that Q1 intersection of Q1 with A is something bigger than Q naught intersection A. Yeah, so we will show that in fact Q1 bar intersection A is non-zero. A bar is non-zero. Okay. So let's take something, some non-zero element in Q1 bar. Since B mod Q naught is integral over A mod Q naught intersection A, we know that this X bar is integral over A mod Q naught intersection A, which we will call A bar. Yeah. So that tells us that there exist AIs such that we have this integral extension where AIs are all in A bar. And remember, A is a domain. Yeah, because Q naught A bar is a domain because Q naught intersection A is prime ideal. Yeah, so we can make sure that A naught is non-zero, because if A naught is zero, you just decrease the you forget about A naught, you factor out an X bar, and you get something of lower degree which satisfies the, and you can cancel out X bar. Yeah, because X bar is non-zero, so you'll get a lower degree polynomial. So maybe you start with a least degree polynomial and get some contradiction. So here we are using, since A bar is integral domain. Yeah. So we get that. So we have this A0 is non-zero, and it belongs. So of course, all X bar belongs to Q1 bar. So everything other than A0 belongs to Q1 bar because it's just linear combinations of X bar, some combination of X bars. So A naught also has to belong to Q1 bar. Yeah. And of course, A naught belongs to A bar. So we get something non-zero in Q1 bar intersection A bar. Hence, Q1 intersection A, which is basically the image of Q1 bar intersection A bar in A, has an element which is not in Q naught intersection. Yeah. So we get this proposition. So that completes the proof of this proposition. Is that okay? So any questions? I hope this is all this is not too fast, yeah, and you guys are able to follow. So let me know if you have some questions. Okay, so I guess this is okay. So finally, we want to prove that dimension A is same as dimension B if B is an integral extension of A. So how do you prove this? You guys are still with me, right?
Yeah. So going up gives one inequality, right?
Yeah, going up gives one inequality. So for instance, if you have P0 contained in P1 and so on, Pm in A prime ideals, chain of prime ideals, then of course you'll get Q0 contained in Q1 contained in QM in B. Sorry, so chain of prime ideals. Yeah, and this inequality will be strict because of what we have, this proposition. Yeah, maybe two of them, two different guys can't map to the same guy. Yeah, so this implies dimension of B is at least dimension of A. Yeah. Now these yeah. So this also yeah. So if you have a chain of prime ideals, then you get a chain of prime ideals, and the fact you can't get bigger chain in B. Yeah, because so if because you can't get two distinct one contracting to the same guy. Yeah, so say let yeah.
So we can just intersect all the QIs with A.
Yeah.
And
so,
is that distinct?
Yeah. So so this was, and so if you have a chain of prime ideals in B, you start with some chain of prime ideals in B, strictly increasing in B, then of course the intersection will give you a chain of prime ideals in A. Is a chain of prime ideals in A. And that tells you that the dimension of A, and they are all going to be distinct. Yeah, dimension of A is at least dimension of B. Okay, so if you take the longest chain, let's say in B, then you'll get a chain of prime ideals in A in which everything is going to be distinct. So that will give you this. And if you take the longest chain in A, then you can lift it to a chain in B. So this is this. So here we are not. So here we are using the proposition, the previous proposition. Yeah, and here we are using going down, going up theorem. Yeah. Okay, so so these two sort of together gives us that the dimension of B is same as dimension of A, rule dimension. Okay, so let's see some example. So maybe I don't know if we saw this localization example. Yeah. So so as I said, you look at you want to look at some example where going up fails or things like that. Then you have to choose a integral extension which is not integral. Yeah. So for instance. Kx contained in Kx 1 over x. So this is not an integral extension, though everything is nice. I mean, both are nice rings. So you can think of it as Kxy modulo xy minus 1 if you like. Yeah. So both are integral domain, finitely generated K algebra, as good as you like. Yeah. They are all both algebrogeometric objects. But going up fails. In fact, lying over itself fails. So, or if you like, going up fails. So you have 0 to x. Yeah. So this is a chain of prime ideals in this ring A. Yeah. So of course, 0 belongs. 0 is a prime ideal in B. So 0. So let's call this B. This is it. So 0 is a prime ideal in B, but we don't have a prime ideal in B which will contract to the prime ideal, in this maximal ideal of A, in fact. So it's a maximal ideal, but anyway, it's also a prime ideal. So is a prime ideal. And any prime ideal and no prime ideal of B, and E is any or Q is any prime ideal of B. Prime ideal of B, then Q intersection A is not equal to X. Why is that? Why can't we have any prime ideal in B which will contract to this prime ideal in A?
Then we will multiply with 1 by X and 1 will belong to Q.
Because X, if X belongs to Q, that means a unit is in Q, yeah? And then Q is, but prime ideals are proper ideals, yeah? So that can't happen since X is a unit. Yeah, so geometrically also you can see what's happening. Yeah, so this is a fine line. The coordinate ring of A corresponds to the line if you like y-axis, x-axis, and this is you know, is if you look at xy minus 1, it will look like a hyperbola, or you can think of it as you know, a point missing from this line. Yeah, and this is your map, sort of like the identity map, except that this point is missing. So so it's sort of inclusion of so the at the variety level, you can think of it as spec m spec of B is an open set of m spec of A, whose complement is the origin. Yeah. So you're just removing origin and rest of the points are there. Okay, so that's how it is. So of course, lying over doesn't hold if you take the origin. There is no point above in m spec B. We can, because it's the inclusion, it's the open subset. Yeah, so you can't capture missing point. Okay. Any questions? So there is something called going down theorem as well, but maybe I don't want to talk about it right now. But I wanted to give you some geometry about the quiz questions, which I forgot to do when I was discussing. If I remember about. So let's talk about geometry here. So what happens here is. What does B mod MB does? What it does is, so you think of it as so this inclusion gives you a map. Yeah, it gives you a map from M spec of so set of maximal ideals of B to set of maximal ideals of M spec of A. Yeah. Or if since here is complex numbers, you know. You are in 3 space, so maybe I can do better. Yeah. So so it's difficult to draw. but in 3 space you get this equation defines a surface. Yeah, so some surface is there in 3 space, so it's sort of difficult to draw, and A corresponds to the complex plane. Yeah, so not the meaning C2, not complex two-dimensional real plane, but C2. Yeah, and and this map is you just look at so the surface is defined by this equation xy cube minus 2zy plus x square plus z cube. So those triples which satisfy this equation, and what you do is you just project onto the x. You just look at the x and z component of the point, and you get this map. Yeah, from so this is your M spec B, and this is your M spec A. Okay, and what does B tensor A mod M does? So let's call this map F. Yeah. So in some sense, so it's not. So it pretty much it looks at F inverse A. Yeah. So you look at F inverse of M. So M is some maximal ideal in M spec A. So it's the point below. So you look at F inverse M. So you'll get certain number of some subset of M spec B. So this M tensor A, B tensor A over B tensor over A mod M is in some sense the ring corresponding to this algebraic subset F inverse B. Yeah. Okay. So if you work with what is called schemes, then this is precisely the statement. Otherwise, one has to do some. So this some changes. So the point is this may not be an integral domain. Yeah. So you are not in the realms of varieties anymore. But when it is an integral domain, then there is a bijection something. So there is some sort of interpretation. Or if you work with schemes, it's not required to be an integral domain. Yeah. So what you're looking at is fibers. Which points of M spec B maps to M? How many points of M spec B maps to M? Yeah. So that is what this measures. Yeah. So the point is, if x is not equal to 0, then it's a degree 3 polynomial. Yeah. And so there are only 3 possibilities for y. And there are exactly at most 3 possibilities. Sometimes the 3 possibilities may become 1 possibility, meaning it may appear with multiplicity 3, but because you get a cubic equation, and a cubic equation can have repeated roots as well. Yeah? So, but somehow the dimension, when you count the dimension, even if it is repeated root, it's okay. So that's why when the maximal ideal does not contain x, then you get that this dimension is 3-dimensional, because there are 3 points lying above any such maximal ideal. If the maximal ideal does not contains x and does not contain z, then this term, the first term, vanishes. Yeah. So x y cube is 0. Yeah, in this plane, in this equation. So you can get only 1 point above. Yeah. And that's why the dimension is 1. Yeah. And so this happens pictorially as well. So on the locus where x is 0, you will see that away from z equals 0, you'll get a bijection between N spec B, where x is non-zero and z is non-zero, and here also x is non-zero. But if both x and z are 0, then there is no condition on M spec B. So y could be anything, yeah, and still it lies in this surface. So x is 0, z is 0, and y anything in this A3C is actually in this surface. Yeah, so y is anything means y-axis. So y-axis is part of this surface, and that whole y-axis contracts to the point x equals 0, y equals 0 in M spec. So that's what happens. So you can see that all sorts of possibilities are there. Yeah. So so that tells you that I mean, and this is an example of a non-integral extension. So when things are not integral extensions, then maybe a higher dimension guy can contract to a point as well. Yeah, so to a lower dimension thing. But when you have an integral extension, such things don't happen. Okay. Okay, so maybe this is all I wanted to talk about today. So I'll end the class now. So maybe first the recording. And if you have some questions, you can ask me. Okay, something's wrong.